Imagine a vast cloud of gas and dust, remnants of ancient stars, drifting through the cosmos. These particles, once part of ancient celestial bodies, now float aimlessly, waiting for a new purpose. This cloud, known as a nebula, is where our story begins. Nebulae are the birthplaces of stars, the cosmic nurseries where new suns are born. Over eons, gravity, the architect of the cosmos, drew these particles together. Gravity, an invisible force, acts like a cosmic magnet, pulling everything towards a common center. Slowly but surely, the cloud began to collapse under its own weight. This collapse is a delicate dance, a balance between the outward pressure of gas and the inward pull of gravity. As the cloud contracted, it began to spin faster and faster, like a figure skater pulling in their arms. This increase in rotation is due to the conservation of angular momentum, a fundamental principle of physics. This swirling motion, a consequence of the conservation of angular momentum, caused the cloud to flatten into a disk, a protoplanetary disk. This disk is a thin, rotating plane of gas and dust, a shape we see mirrored in countless other star systems across the universe. These disks are the blueprints for solar systems, each one a potential cradle for new planets. This spinning disk, known as a protoplanetary disk, became the cradle of our solar system. Within this disk, the building blocks of planets began to form. Within its depths, the seeds of planets were sown, destined to coalesce and evolve over billions of years. These seeds, or planetesimals, collided and merged, gradually growing into the planets we know today. This process, known as accretion, is a slow and steady journey from dust to worlds. The protoplanetary disk wasn't just a flat structure. It was a dynamic environment, a whirlwind of gas and dust particles in constant motion. This motion, governed by the laws of physics, played a crucial role in shaping the destiny of our solar system. As particles collided within the disk, they exchanged energy and momentum. Some particles lost energy and drifted towards the center, eventually clumping together to form the protostar that would become our sun. Others, with more energy, remained in the disk, orbiting the central star. This process of accretion, the gradual accumulation of matter, continued for millions of years. As particles clumped together, they formed larger and larger objects, planetesimals, the building blocks of planets. As the protoplanetary disk spun, two opposing forces came into play: gravity and centrifugal force. Gravity, the force that attracts all objects with mass, pulled the particles towards the center of the disk, towards the growing protostar. Centrifugal force, on the other hand, acted outwards, pushing the particles away from the center. This force arises from the inertia of the particles, their tendency to move in a straight line. In the rotating disk, this inertia manifested as an outward force, counteracting the inward pull of gravity. This delicate balance between gravity and centrifugal force was crucial for the formation of planets. If gravity had been too strong, the entire disk would have collapsed into the central star. If centrifugal force had dominated, the disk would have flown apart, scattering its contents into the void. Staying the course, the importance of angular momentum. Another crucial factor in keeping the protoplanetary disk from collapsing was angular momentum. Angular momentum is a measure of an object's tendency to keep rotating. The faster an object spins and the more mass it has, the greater its angular momentum. The protoplanetary disk had a lot of angular momentum, inherited from the original cloud of gas and dust. This angular momentum acted like a stabilizing force, preventing the disk from collapsing inward. As the disk evolved, this angular momentum was transferred to the planets forming within it. This is why the planets all orbit the Sun in the same direction as the original disk's rotation. Order from chaos. How planets cleared their paths. The early solar system was a chaotic place, with planetesimals whizzing around in all directions. Over time, however, gravity began to impose order on this chaos. Larger planetesimals, with their stronger gravitational pull, attracted smaller ones, gradually clearing out their orbital paths. This process, known as accretion, led to the formation of the planets we see today. As planets grew, their gravitational influence increased, further shaping the structure of the solar system. The planets' orbits weren't perfectly aligned, but they were all confined to roughly the same plane, a testament to their shared origin in the protoplanetary disk. A well-organized neighborhood, the structure of our solar system. Our solar system is a fascinating and complex arrangement of celestial bodies, each playing a unique role in the cosmic dance around our sun. The result of this billions-year-long process is the solar system we know today. A well-organized neighborhood of planets, moons, and asteroids, all held together by the gravitational pull of the sun. This intricate system has evolved over time, shaped by the forces of gravity, collisions, and the dynamic processes of star formation. All these celestial bodies orbit the sun in a relatively flat plane, which is a remarkable feature of our solar system. This flat plane is not a random occurrence, but a result of the angular momentum conserved from the rotating disk of gas and dust that formed our solar system. This plane, known as the ecliptic, is a testament to the shared history of our solar system. It serves as a cosmic record of the early days of our solar system, providing clues about its formation and evolution. The inner solar system is home to the rocky planets, Mercury, Venus, Earth, and Mars. These terrestrial planets are characterized by their solid, rocky surfaces and are relatively small compared to the gas giants. These planets are thought to have formed closer to the Sun, where the intense heat vaporized most of the lighter elements, leaving behind rocky materials. This process led to the formation of dense, metal-rich cores and silicate mantles, giving these planets their distinct characteristics. The outer solar system is dominated by the gas giants, Jupiter, Saturn, Uranus, and Neptune. These planets are much larger than the rocky planets and are composed mainly of hydrogen, helium, and other volatile compounds. These massive planets formed in the colder outer regions of the protoplanetary disk, where temperatures were low enough for gases and ices to condense. This allowed them to accumulate vast amounts of gas and ice, leading to their enormous sizes and thick atmospheres. The process of accretion in these outer regions was crucial for the formation of the gas giants. As they grew, their strong gravitational fields attracted even more material, including moons and rings, which now orbit these colossal planets. This dynamic and diverse structure of our solar system continues to captivate scientists and astronomers, offering endless opportunities for exploration and discovery. Cosmic exceptions, when planets dare to be different. While most planets in our solar system orbit in a relatively flat plane, there are a few exceptions. Pluto, for example, has a highly inclined orbit, tilted at an angle of about 17 degrees to the ecliptic. These exceptions are thought to be the result of gravitational interactions between planets in the early solar system. For example, Pluto's unusual orbit may have been caused by a close encounter with Neptune billions of years ago. These exceptions highlight the dynamic nature of our solar system, a place where gravity continues to shape the orbits of planets and other celestial bodies. A universe of possibilities, exploring planetary systems beyond our own. The study of our own solar system has provided us with a framework for understanding planetary formation. But it's important to remember that our solar system is just one of billions in the Milky Way galaxy. As we explore other planetary systems, we're discovering a staggering diversity of worlds. Some with multiple stars, others with giant planets orbiting incredibly close to their host stars. These discoveries are challenging our understanding of planetary formation and reminding us that the universe is full of surprises. If you enjoyed this video, check out what planets were like 3 billion years ago.